Hello and welcome to this session on nuclear fission. So what we're going to do today is we're going to look at the process of nuclear fission, what it is, how it works. We're going to describe what's meant by a chain reaction. We're going to state how fission produces energy. We're going to describe the roles of parts in a nuclear reactor, so the different parts of the reactor, what they do. And then we're going to look at the advantages and disadvantages of nuclear fission. So the basics to start off with, you need to know how a general coal power station works. So what they have is they will usually have a fuel, so maybe coal or gas. They will burn it and that will make heat. That heat is then used to heat water. That water will then turn to steam. The steam will then go to the turbines. Turbines are like big fan blades, huge fan blades. They turn around because this steam is pressurized. It turns the turbines, which is connected to a generator. The generator is a magnet and a coil. They will spin inside one another. And when that happens, it will cause a current to be made, an alternating current. A bit of a misconception people have, mainly about the drawing that I've got on the board here, is the fact that when you burn coal, it makes carbon dioxide, and then that carbon dioxide turns a turbine. Or when you burn coal, that makes steam, and that turns a turbine. The burning coal makes heat, that heats water to make steam. And this condenser, the job is that it will recycle that steam back again so they don't have to keep replenishing the supply. So this is a basic nuclear reactor. So in the nuclear reactor, we've got a few things. It looks very, very similar to the last one. So you've got the generator here. When that turns around, it will produce an alternating current. You've got turbines that spin. They're spinning around because water is turned into steam that's going around here. And that steam is recycled via this condenser over here. But instead of having coal that's burned to produce the heat, we use a nuclear reactor that contains a fuel. Now, this fuel that we use is usually uranium, but it also can be plutonium. The uranium isotope that it uses is uranium-235. Uranium-238 isn't as good in a fission reaction as uranium-235. So do try and remember uranium-235. Another fuel they can use is plutonium-238. Now what they normally do is instead of making these into solid rods, they will turn these into like pound coins, if you like, really thick little cylinders. People forget that uranium is a metal. When you look at it, it's not like on The Simpsons where it's glowing green, it's a metal. So they'll turn them into these little pellets, and then they'll put these pellets into tubes, like you see in this diagram here. And then in these tubes, they will put loads of them together, and that is a fuel rod. So in the reactor, they have these fuel rods, which are represented by these bits sticking in. Now what they'll do is, in order to produce heat, these uranium nuclei, they will decay because they're very, very unstable. And when they decay, they will decay into something smaller and they give out radiation, but they also give out energy, such as heat. The problem is that if you just had a source of uranium-235, the rate that it produces heat energy is not that great. It's not very high. And that's a problem because we want to make heat at a larger rate so that we can make steam at a larger rate so we can turn the turbine quickly to produce electricity to meet demands. So what we need is we need a source of heat production that's at a very high rate. So this uranium or plutonium makes heat, but we need it to make heat quicker. So what we need to do is we need to force it to decay, which is where nuclear fission comes in. So this, if you like, is nuclear fission, where we're forcing those unstable nuclei to decay. So what happens is we take something like a neutron, we use a neutron and we fire it at a uranium nucleus. Now it's really important you use the word nucleus and not atom, because electrons are not involved here. It's just the nucleus. So we fire a neutron into a uranium nucleus. Can't spell. There we go. We fire a neutron into a uranium nucleus. And what happens is that when that uranium nucleus absorbs that neutron, again, another key word. When that nucleus absorbs a neutron, it becomes bigger, it becomes more unstable, and it might decay. And when it decays, it will do something like this. Now, as you'll see, when it decays into roughly 2 nuclei. They're about the same size as each other, If you like, literally the nucleus is split into two. And when it does that, it releases energy in the form of heat, and that's good. We can use that heat in order to heat the water to generate steam to produce electricity. Also, it produces these little things here. You might notice these things are more neutrons. So what we can do is we can look at where these neutrons are going to go next. One thing I wanted to look over was why we're using a neutron in the first place. Why can't we use something like a proton or an electron? The main reason why we use a neutron is because a neutron is neutrally charged, i.e. it has no charge. Therefore, when it comes to interact with this nucleus, which is positively charged, it will have no electrostatic interaction. It won't be repelled or attracted. Therefore, it will be more successfully absorbed. So just to recap, a neutron is fired into a uranium-235 nucleus. It is absorbed, and that makes it more unstable. And because of that, it will decay. And when it decays, it splits into two roughly equal size smaller nuclei, as well as making heat energy, which we use to produce steam, and 3 neutrons. In essence, that's what fission is. We're turning a large nucleus into smaller nuclei, breaking it up by using a neutron. Now, these neutrons, what they'll do is they'll then find their way into other uranium nuclei. They'll then be absorbed, they'll become unstable, and they'll then break up, and each one of those will produce 3 more neutrons. So if you think about it, if we have this one to start off with, that one neutron goes in, it breaks these up, and the 3 neutrons come out. This uranium nucleus is going to split up as well as it does in fission, and this one will, and this one will, and each one of those will produce 3 neutrons. So now we've gone from having 1 neutron starting off the reaction to having 9 neutrons. They'll then go into 9 different nuclei, and those 9 nuclei will then decay, and then you'll get 27. So what you've got is this thing called a chain reaction, where one reaction is setting off another. Now this can be quite a good thing, because what you've got is this reaction sort of self-sustaining itself. We don't have to keep firing in neutrons. The reaction is carrying on by itself. This can be a bad thing though, as you've probably heard about things like Chernobyl, where if we don't control the reaction, if the rate of neutron emission is too high, then what's going to happen is the rate of fission reactions is going to be very high, producing a lot of heat in a very short amount of time. It can lead to something like an explosion, and it can lead to things like a core meltdown where the fuel will actually melt. Very, very dangerous stuff here, which we don't want to happen. But you know what? We might want it to happen. In the case of these things, nuclear bombs, like the ones dropped in Hiroshima, if we have a nuclear fission reaction that's not controlled, that can happen very quickly, we can release a lot of energy all at once. So if you like, sometimes it's maybe not a good idea to control it because we want to release energy all at once, but in terms of safety, we do need to control it. So that's what's meant by fission and what a chain reaction is. How fission produces energy? Well, this is just a very easy question you need to answer. Very quick recall. In the spec they say you need to know. It's via this thing. You may have heard of it. Albert Einstein came along with this equation, E equals mc squared. Essentially what happens is that when you get these nuclei decaying into smaller nuclei, a tiny, tiny bit of mass is actually lost. It seems really weird, but some of the mass in these nuclei are lost. We're talking times 10 to the minus 27 kilograms, hardly anything. But where does that mass go? Well, that mass is converted into energy. And Einstein, we'll not go into the complications, Einstein said that energy and mass can be converted from one form to another. That mass is converted into energy via this equation. So if we look at this equation, E equals mc squared, E stands for energy, M stands for mass, and C stands for the speed of light in a vacuum. So if we said, I don't know, 1 times 10 to the minus 27 kilograms, hardly anything, that's one nucleus decaying. Let's just see how much radiation is given off by that. 3 times 10 to the 8 is the speed of light in a vacuum. If you work out how much energy is given out by that, it is a massive amount. 9 times 10 to the minus 8 joules. Now that might sound like an amount, but that's just by one decay, and there are a lot of decays going on very quickly. They use hundreds, if not more than hundreds, thousands of tons of this uranium fuel in a reactor. If all of that went at once, that is a massive amount of energy. But that, in simple terms, is where the energy comes from. Mass is converted into energy. That's where you get the energy from. So let's look at the parts of a nuclear reactor. So nuclear reactor, this one here, it's slightly different to the last one. It's the same essence, if you like, that you've got heat that's been taken away from these from the fuel rods. In this case, what they're doing is they're heating up gas, which then heats up water, which will then go to make steam to turn turbines. But it's the same thing. So what we've got here, a few things you need to know about. In between these uranium fuel rods, you have control rods. They're made of a material called boron. Now what they do, boron is very good at absorbing neutrons. And when they absorb neutrons, it means that the fission reaction won't be able to happen because there's no neutrons around to be absorbed by uranium nuclei. So if you think actually this fission reaction is getting out of control, what they'll do is they'll insert the boron control rods. They'll go between the uranium fuel rods, absorbing free neutrons, slowing down the reaction. Okay, so boron control rods, they slow down the reaction, they control the reaction by absorbing excess neutrons. We've got this thing called a moderator. Now, they used to be made out of graphite or more water. These days they're made of. If you ever watch Chernobyl, graphite is what they are made of from. Water, what it does is that the neutrons that are emitted in these fission reactions, they're moving very, very fast. They've got a lot of kinetic energy. And that is actually a bit of an issue because if they've got a lot of kinetic energy, they're not going to be easily absorbed. I tried to model this by saying, like, imagine I'm trying to throw a ball for you to catch. If I throw it too fast, you're not going to be able to catch it. So what happens is this water absorbs some of the energy from the neutrons, making them slower. Therefore, they can be more easily absorbed by the uranium. So therefore, fission reactions are more likely to happen. The final part is the reactor casing. So the reactor has quite a thick casing made out of concrete. A couple of reasons it has that. Main thing is to support the whole thing. Bit of common sense here. This reactor weighs tons, thousands of tons. It needs a lot of support, so they need to use very, very thick concrete, meters thick, in order to support it. But also, it's to absorb radiation. We don't want that radiation going to the surrounding environment. We do not want people being exposed to that radiation that work in the power station or that are nearby the power station. So we need concrete. Alpha is not going to go through concrete, beta is not going to go through concrete, gamma is going to be heavily reduced by that concrete, so that's why we have it. It's usually reinforced as well to make sure that if there are any problems, it does keep its structure. Final part, describing the advantages and disadvantages of nuclear fission. So here are the advantages. So we've got no greenhouse gases being produced. You need to word it like that, no greenhouse gases. Okay, don't just say nothing dangerous produced. No greenhouse gases. That's a good thing because then we're not getting carbon dioxide produced, for example, which means that we've not got things like the global warming being contributed to. So that is a positive. High power output, a lot of energy can be produced by nuclear fission, which is why we're very, very interested in, and plenty of fuel. We've got quite an abundant source at the minute of uranium. Disadvantages, nuclear waste. Now the problem is that once we finish with a nuclear reactor, which is between sort of 60 and 100 years at that, once we finish with this, the fuel is depleted, i.e. it's still radioactive, it's still giving out radiation and heat, but the rate that it gives out heat is not high enough for what we need. So we need to replenish it with fresh uranium. So what do we do with it? Well, what we've got to do is we've got to store it. We store it underground, we'll store it in secure bases, in things like sealed ceramics, concrete, etc., to make sure the public cannot get access to it. It needs to be secured, it needs to be sealed to make sure that your everyday person can't get anywhere near it and can't expose themselves, can't contaminate themselves. We don't want things like the water supply being contaminated, because then that can lead to deaths. We do not want the environment around us being contaminated either. It's not that if people could access this, they could use it for bombs. A lot of people do think we could use this for a nuclear bomb. We can't. What some people could do, though, is they may want to use it for poisoning techniques. So you could poison the water supply with it, for example. It's non-renewable. We cannot make any more uranium. People find that one hard to believe. They think it's renewable. We have only got a certain amount of finite source of uranium or plutonium. It is technically finite. It is non-renewable. The power stations are very expensive to build. I mean, once they're built, the costs are fairly low, but building the power station, as I was saying earlier, it needs to be very, very secure, and it needs to be using meters of concrete there just for the reactor itself. It's very, very expensive. And then we've got to pay for it to be stored and transported afterwards. The whole nuclear power station needs to be stored, if you like, afterwards. They take it apart brick by brick because it's contaminated with the radioactive material that's been in it. And then finally, accidents. I mean, this is what everyone talks about when we talk about fission. It can lead to accidents. There have been a few in the past. Obviously, things like coal power stations, you can have accidents, but the accidents here are very, very severe. In Chernobyl, where reactor 4 exploded, it didn't kill many people at the time, but it could have killed a whole lot more people than it did. As they've said in documentaries, they can't actually assess how many people itself potentially have been killed by this, but the amount of radiation spread around Europe was incredible. Mountain on in Wales and Mount Snowdon, they detected radiation on there after Chernobyl happened. Terrible thing. So this is one of the major disadvantages of it. Cool. I hope you enjoyed, and see you next time. Bye bye.